Hello, researchers and engineers. This is Renzi Liu from Shanghai. I'm working as a municipal engineer at DHI China. My topic today is leakage detection and isolation in water distribution network based on data mining and genetic optimized hydraulic simulation. My colleagues, municipal engineer Zhen Zhang, data mining analyst Dian Zhang, and I have been working on this competition together. We're glad to have this opportunity sharing our work. I'm going to first talk about our methodology, which is the main part of this presentation. It has three parts: hydraulic model calibration, data mining, and leakage isolation. And then I will talk about the results we have. The technical rods is shown on this slide. We applied three models: uh, the Elton hydraulic model, some data mining models, and leakage isolation model. We first did some calibrations of the hydraulic model with scanned data to make the model more accurate. Then we ran leakage simulations numerous times with this calibrated model to enlarge our dataset for training the data mining model. Once the model is well trained, it is used for prediction. The prediction made by this data mining model gives the leakage area and a leakage time period. Given these results, the leakage isolation model is applied eventually and could isolate the exact leakage location and time point. So 5 parameters are considered in hydraulic model calibration: demand patterns, demand seasonality, pipe roughness, base demand, and effective diameter of pipes. There are 6 user categories in L10, as we all know: residential, commercial, and for industrial users. Each of them has its unique demand pattern. We use the demand meter readings from 82 AMRs in Area C to calculate these patterns. The multiplier of category C at time t equals to the sum of all n demand meter readings of this category at time t divided by the sum of all readings all n demand of all readings at all time steps. These figures show how demand patterns vary with different categories. The residential and commercial demand patterns basically follow a weekly routine with similar daily variations. Industrial user 1 is better described by a 13-day pattern, and industrial user 3 is better described by a 12-day pattern. Industrial 2 and 4 have a weekly pattern, but the daily demand pattern is much different from one day to another. We also calculated a seasonal factor for different user categories of different months during a year, which equals to the average demand of a month divided by the average demand of the whole year. When we ran simulations of a certain month, we apply these factors to their base demands for different users, and then we ran simulations. For parameters as pipe roughness, nodal base demand, and effective pipe diameter, we apply genetic algorithm and run APNet iteratively to solve this optimization problem. The variables are these twitching coefficients of residential demand, commercial demand, pipe roughness, and pipe effective diameters. The variables are constrained to vary in a certain range defined by the problem statement, and the objective function is to minimize the loss between the measured and simulated pressure values. We ran the algorithm with different populations and generations, and these two combinations of coefficients are applied in the hydraulic model. For the data mining part, we mainly use the pressure data as our training data set. The 2018 scanner data has 33 pressure sensors data for 1 year, but there's only 10 known leakages in this data set. So we made up some more data with our calibrated hydraulic model. To do that, we randomly simulated 5 different leakages near each sensor for 7 days in 14-day hydraulic duration. So after that, we will have a huge dataset with all kinds of leakage situations to be learned by the data mining model. And we build the feature matrix in this way. We set a referential value for each sensor, which is about 95% above its minimum level. And at each time step, we calculate the difference between its measured value PAST and the reference as.pst. Then at each time step, we clip the dataset by a 1-hour window and calculate the average delta PAST as the final feature value. The label vector has n values. Each time step has a label referring to leakage or not. So we label 0 as no leakage at time t, or we label a number s as leakage near sensor s at time t. The label is determined in this way. For simulated data, we know that the sensor numbers since we simulated them in EPNet, so we just label them. For the scanner data, we check the pressure data of each sensor and label the sensor number, of which its scaled pressure changes most during the reported leakage period. For example, for this reported leakage, the possible start time is at this time point. So after we check all sensors pressure data of this time period, if this deficit is the largest, we then label N2 to 9 from this time point to the reported repair time point. So for example, we label N2 to 9 from TK somewhere between here to TM, we label N2 to 9. So once we have the feature matrix and label vector, we can use them to train our LSTM and light GBM models. So given the predicted results from our data mining model, we can use the genetic algorithm-based leakage isolation model. So leakages are simulated iteratively in EPNet using the calibrated L-time model, and the pressure results will be then compared with the measured data, and the most matched simulation indicate that the possible leakage event exists. The variables here is the index of the leakage node and the emitter coefficient of this node, and it is also constrained by a maximum emitter coefficient, and pressure at the nodes should be non-negative, and there should be only one leakage at one node at a time. And the objective function is to minimize the observed head and the simulated head at all junctions and all time step. As for the results, for the data mining part, we use 20% of the 2080 measured data as validation dataset and all other data as our training dataset. These two figures show the training and validation loss of the two models, LSTM and GBM. So basically, the models perform pretty similar on both training and validating dataset. The output of the models are predictions of labels at each time step. So we check the results and wrapped up a table for better understanding. So these are the 10 reported leakages in 2018, and the sensor IDs are the nearest sensors to their corresponding leaking pipe. What the model predict are the leakage start time and repair time. We could find the predicted repair time is pretty close to the reported ones. Then we ran leakage simulations to isolate the leaking location. So the results is showing here as node ID. If we check them on map, so the predicted leakage nodes and the actual leaking pipe in 2018 are actually pretty close to each other. So the accuracy is not bad. Good news for us. The same procedure is also applied for 2019 dataset, and it gives out several possible leakage locations, like shown here in the time. That's all for our sharing. Thank you for your time listening, and thanks for the Battle DIM committee providing this opportunity. We've been learned a lot working on this competition. Best regards to all participants. Bye bye.